I'm here with you today to speak about the Math Task program. And the Math Task program is a program that it is part of the activities of the Research in Mathematics Education group at the University of East Anglia in Norwich, where I'm based. Before starting, I would like to say a few things about the Research in Mathematics Education group, because this is my home. This is the group that hosts all these activities, including Math Task. It is a group that is specialized in mathematics education. It started in 2003, so this year we celebrate 20 years. Our activities cover a range of areas and educational levels, from primary, secondary, and tertiary mathematics. And it is our group leader is Elena, who is with us today. I try to use my buttons, but it seems that they don't work. Okay, this is Elena, and she's the leader of the group. And through the activities in the group, and specifically with Math Task, we have collaborators in different places of the world. I can name some of them: in Canada, in Brazil, in New Zealand, in Tasmania, in Australia, in Tunisia. So we have activities in different parts of the world, and given that we are coming from a different educational system, personally I'm originally from Greece, we have open eyes to see the differences between the educational systems, and we try to address such differences in our work. Before starting, I would like to say that I have uploaded some of the examples I will use today in Padlet. You can scan the QR code, or you can type the link, or you can find this link in the seminar website. This is just for you to have an easy access to the materials instead of looking at my screenshots. And also, if you want to share some thoughts, or if you want to type some ideas as we go through the materials, you can use Padlet, one more digital platform for our communication. So after this introduction, this is what I'm planning to do today. I have planned first a brief introduction to Math Task, the Math Task program, with an example, and then we will go through the theoretical principles underpinning our work and some theoretical constructs that have emerged from the use of Math Tasks. Then I have prepared an example of a Math Task for working in our group. So I will invite you to do some work or do some thinking, and then if you want, you can share your thoughts in our discussion. And we will close the session with a discussion, and as Barbara said, during the discussion we will switch off the recording. So what is Math Task? We will start first from what has inspired the work on Math Task. As we know, mathematics teachers want their students to understand, appreciate, and enjoy mathematics. But very often, what they face in the classroom is nowhere near these high aspirations. Students' responses may not make sense, addressing individual needs is difficult, the class does not cooperate, technology is confusing, and the resource is not exactly what is needed. So in practice, very often, teachers face situations which are obstruct their high aspirations. So in math task, we start with findings from research that shows that engaging teachers with fictional challenging situations before they actually face those situations in the classroom is an effective start. And the discussion of specific classroom situations is more productive than a theoretical and abstract conversation. So with this in mind, we design situation-specific tasks. This is what we call math tasks that emulate challenging classroom situations, and we engage teachers with those tasks either individually or in groups, either in writing or in discussions, and in a productively reflective setting of school or university-based workshops. A math task always starts with a mathematical problem and a critical incident in a classroom that occurs as students and teachers are working towards solving this problem. So in practice, a problem is given to the students and then something is happening. But instead of describing it in an abstract way, let's make it specific. So let's have a look at the math task. I will start with the problem first. This is, you can see on your screen the problem. If you log in on Padlet, you can see the whole math task. I will project the QR code in the next slides, but let's have a look at the problem first and familiarize ourselves with what the problem says before going to more details. We have two columns of numbers, and the question is, can you make the two columns of numbers below add up to the same total by swapping just two numbers between the two columns? Explain why or why not you can or you cannot do that. Shall I take 1 minute just to familiarize ourselves with the problem? You can think, you can try to solve it. Just 1 minute. Does anybody want to share a thought about the potential response to this problem? Eben?
Well, I mean, what do you want us to solve it mathematically, or? You can start by adding up the sum, the total, and then if you have to have the same in the two columns, it should be an even sum. So that's probably the simplest approach to quickly show that that wouldn't work. The alternative is to add up each column, and then you look at the difference, and you notice that the difference is an odd number, but every time you swap around stuff, the difference would be added in the one side and subtracted in the other, which means that the difference should be an even number, which again doesn't work. Are you looking for more solutions, or?
No, that's okay, perfect, right. Actually. That's perfect. Thank you so much. So in practice, there is no solution in this problem. One explanation, one potential explanation is what Eben suggested, that if we want to make the totals of the two columns the same, we have at least to split the numbers to two equal parts. But the total of those numbers is an odd number, or the difference of the two columns, of the total of the two columns is an odd number. So it's not possible to make this arrangement, regardless of what the numbers are in each one of the cards. So in practice, the problem does not have a solution. But as Eben asked, do we expect a different justification? I don't know yet, depending on the class, depending on the student's background. There are different ways of explaining this problem. I will go to more details in the next slides, because this is one of the reasons we have chosen this problem for this situation. But I will move now to the situation we have constructed on the base of this problem. So we see here that the teacher gave this problem to a year 7 lesson. And then we see a dialogue exchanges between 4 students, Khalil, Mel, Wendy, and Callum, who approach the problem in different ways. If you want to download the whole math task, you can go to the Padlet, click scan the QR code, or you cannot click the link, I think on your screen, but the link is in the seminar website. I will go through this structure to explain you how we designed it, why we designed it, and our rationale behind the choices of the students' responses. The responses are fictional, but they have been inspired from research and practice. So first, the overall structure of the math task. We start with a mathematical problem, and then we have the dialogue between students who solve the problem, and this is the two of them make the classroom situation, what we call a classroom situation. And then there is a set of questions that are for the teachers or for the participants to solve the problem first, to reflect on how they would respond to the students, and to interpret the situation and respond to the students, and in this specific case, to go beyond this task in terms of the opportunities to develop reasoning skills in their class at year 7 or at a different level. When we designed this task, we had in mind the development of students' reasoning skills. And this is the reason we called this the reasoning math task. So I will step back a little bit and say a few things about the design principles we use when we designed a math task. First of all, it has to do with the mathematical content, the mathematical aspect of the problem and what is happening in the classroom. This content concerns a topic or an issue that is known for its subtlety and for causing difficulty to students. We know this from literature or from previous experience. Usually, we know this from both. Some useful theoretical constructs that put attention to this, to the identification of a topic, is the work from Litham, Peterson, Stockero, and Van Zest on the mathematical significant pedagogical opportunities to build on students' thinking, what they call MOSTs, which is exactly points where they offer opportunities to address students' thinking. The student response that is reflected in this situation should reflect those responses should reflect this subtlety or lack or difficulty, and provides opportunities for the teacher to reflect on and demonstrate the ways in which they would help the students achieve this subtlety or overcome the difficulty. So this is the element of the pedagogical opportunity which is highlighted in in most. Then teachers' pedagogical approach concerns mathematical, pedagogical, and epistemological issues that are known for the subtlety or for being challenging to teachers. Terms that, theoretical constructs and terms that have been used in the literature related to these challenges to teachers and teacher decisions are the work from Herbst and colleagues on the practical rationality of teaching. The spectrum of warrants, which is it's coming from the work of Nardi and colleagues, that see the challenges to teachers in the context of classroom situations. I will return to this point later in my slides. But also, the mathematical content and student-teacher responses provide a context in which teachers' knowledge, beliefs, and intended practices, mathematical, pedagogical, epistemological, are allowed to surface. Again, there are some work in the literature that can inform us in the way we see such approaches. Works related to the mathematical knowledge for teaching from the work of Deborah Ball and her colleagues, the horizon knowledge, especially from this work, and also the knowledge quartet, the work of Tim Rowland and his colleagues. So going back to this math task, the reasoning math task, in this version, you can see on your screen, we specified the level. We said that it is a year 7 lesson. The reason we have chosen year 7 is because year 7 in the UK educational system is the beginning of secondary education. So that contextualize it at this level allows us a discussion on students' transition from primary to secondary education. And we have used this activity with groups of teachers, a mixed group of teachers from primary and secondary, and it worked very well. There are alternative options. The year level can stay open, and participating teachers can choose the educational level of their choice. Because in practice, the problem can approach differently in different educational levels. Iben actually asked this when she proposed a potential approach to the problem. If we want more justification or different approaches to the problem. And it is true that this problem can be approached in different ways. Now, the choice of the problem. It has been chosen because, as I said, it can be approached by both primary and secondary teachers and students. It has the potential for expansion from elementary arithmetic to generalization of number facts. For example, when the discussion goes around the odd and even numbers. Finding the right pair of numbers, if it exists, triggers exploration routines, which can vary across educational levels and within educational levels. For example, we can see some of those routines in the responses of the students in the math task. The question, explain why or why not, triggers substantiation routines. For example, reasoning that again vary across educational level and within educational level. The problem in this case does not have a solution, which challenges the view that every mathematical problem should have a solution. The value of the problem relates to the explorations and substantiations rather than to performing a routine that will give a result. The problem has the potential for further generalizations or generation of other problems by teachers and students. For example, is the problem solvable if the total of the columns is an even number? I will leave this question open. It is actually, it's not sure if the total is even that the problem will be solvable. Can we change the numbers to make the problem solvable when we spot that it's not? Can we change the numbers in order to have more than one solutions? So the variation of alternative problems above can serve purposes of differentiation, the mathematics classroom. When we have a classroom of mixed ability, this problem might be appropriate for some students, might be too difficult, might be too easy for other students. So having a range of problems in the same spirit helps to address different students' needs. But let's have a close look on the responses of those 4 fictional students. First of all, Khalil. Khalil's approach is explorative with trial and error. This is a good start. First of all, Khalil engages with the task. However, he may need a hint to observe that some of the pairs would not work and they can be omitted, as we see in Mel's response that follows. So with Khalil's response, we try to shift the attention to a trial and error approach without a strategy. Then with Mel's response, which is also explorative with trials, but without trying all the pairs. So it seems that her approach is more strategic. It would be good, such strategic approach, to be commented and shared with the class. A strategic approach may have the potential to lead towards a general observation about the numbers in the 2 columns, as we see in Wendy's approach. Wendy not only puts forward a conjecture that is no solution, so this is a type of abductive reasoning. It's not a certain conclusion. She says, maybe it can't be done. But from observation on the relationship of the numbers, potentially through what the previous students have done, she proposes a more general explanation. If the difference is odd number, we cannot identify a pair of numbers. Or an alternative argument that may emerge is that if the total of numbers is odd, we cannot identify a pair of numbers. There is an opportunity here to extend the discussion to arguments such as when the total of 2 columns is odd or even, the difference of the 2 columns is odd or even, and how can we justify such arguments? Or if the total or the difference is even, can we identify a pair of numbers that would work, etc. And then we have Callum. Callum represents the type of student who does not engage with an activity without a clear course of action. He does not see the point of the exploration, especially when there is a risk of not finding a solution. Callum's response aims to trigger a discussion around views of mathematics as a set of predefined steps that always lead to one and correct response, or affective issues of students' reluctance to engage with explorative activities. So, up to this point, I demonstrated an example of math task, and I demonstrated also our rationale, our thinking behind this design. For the next part, I will try to highlight some of the theoretical principles underpin our work and some of the theoretical concepts that have emerged from our use of math task. But before moving to the next part, is there any question, any comment, anything that you would like to ask or share? Okay, I'm moving on. Let's let's start with our theoretical perspective as it stands now, because math task has been through several steps since the first ideas and the first tasks came together. As we stand now, our perspective is discursive, and we draw on the theory of cognition. According to this theory, mathematical and pedagogical discourses are established in communities and reflect the practices of those communities. So we try to take a distance from work in research, in the literature that stays on teacher knowledge, and especially we try to take a distance from works that criticize teachers for the lack of such knowledge. We think that criticizing teacher knowledge is not a productive way, because very often teachers make decisions for several other reasons. Sometimes they are aware that they may compromise the mathematical rigor of their response to the benefit of their pedagogical aims. So we are interested in this balance between the mathematical and the pedagogical part, which is related to teachers' work, and we try to see this in the context of the communities and the institutions teachers act. And to make this more specific, I will draw on a statement from one of the participants in our research. When we asked this participant to discuss a situation, that was a situation from calculus, when there was a graph on functions, and the question was whether the teacher would accept a graphical argument from a student, a visual argument, without the algebraic justification. So when we asked the mathematics teacher if they would accept a graph-based argument as a proof, he replied, "Mathematically, in the classroom, I would welcome it at lesson level, and I would analyze it and praise it, but not in a test." We asked the teacher to elaborate, and he said, "Through the graph-based argument, I would try to lead the discussion towards a normal proof with the definition, the slope, the derivative, etc." And when we asked to justify, he said, "This is what we mathematicians have learned so far, to ask for precision, to have this axiomatic principle in our minds. And this is what is required in the exams, and we are supposed to prepare the students for the exams." This quotation is coming from a work that was published in 2009 in the Journal for the Learning of Mathematics, and inspired a later work on the same data. Let's have a close look at those responses from this participant. This teacher seems to approach visual argument from three different and interconnected perspectives. the restrictions of the current educational setting, in this case, the university entrance examination, the epistemological constraints with regard to what makes an argument a proof within the mathematical community, and finally, the pedagogical role of visual argumentation as a means towards the construction of a formal mathematical knowledge. So these three perspectives reflect three roles from the mathematics teacher that they need to balance. The role of the educator who is responsible for facilitating students' mathematical learning, the role of the mathematician who is accountable for introducing the normal practices of the mathematical community, and the professional role, according to which they are responsible for preparing candidates for one of the most important examinations of their student career. So the argument of seeing teacher practices and responses in the context of where they act, the institutional context, and the communities they belong, is more productive to understand what they say and the complexity of their work, instead of talking about their knowledge, the lack of this knowledge, or the proficiency of this knowledge. Those observations led us to characterize teachers' arguments. We drew on the work of the Toulmin's work, who proposed a model of informal arguments, but also on Freeman's work that offered the classification of the warrants on those arguments. And that helped us to classify the arguments that mathematics teachers put forward. Their warrants might be a priori warrants, resorting to a mathematical theorem or definition. This is what we call an a priori epistemological warrant. For example, when they say that this is the way we do it in mathematics, and this is coming from the such theorem, etc., or resorting to pedagogical principles. This is what we call a priori pedagogical warrants. For example, when the teachers say that it is using a lot of examples or engaging the students with a discussion will help their learning. But also, we identify what we call institutional warrants, which is a justification of a pedagogical choice on the grounds of this choice being recommended or required in the textbook. And this is institutional curricular warrant. For example, when they say that this is what is asked in the exams, and I will do this to prepare the students, or the grounds that it reflects the standard practices of the mathematical community, which is institutional epistemological warrant, when they say that in the mathematical community, we have to justify this response with a proof, for example. But also we identify empirical warrants. The citation of a frequent occurrence in the classroom, according to the arguer's teaching experience. This is what we call empirical professional. When the teachers say, for example, that they have seen this happening several times in their classroom, or resorting to personal learning experience in mathematics, which is empirical personal warrant. When they say that when I was at the university, I had problems with tangents, for example, and I expect my students to have similar problems. And finally, evaluative warrants, which is a justification of a pedagogical choice on the grounds of a personal held view, value, or belief. To give an example for this warrant is when the teachers say that, oh, now students do not want to engage with the mathematical activity because they have learned to find everything ready-made online, and they don't want to work further on a task. So that helped us to see the complexity of where some of the arguments teachers put forward, where they're coming from. So I'm going back to our theoretical underpinning in our work, and I will try to elaborate what we mean by mathematical and pedagogical discourses. In terms of mathematics teaching, we see mathematics and mathematics education as distinctive discourses. And learning of mathematics and learning about mathematics education is a communication act within these discourses. So we find ourselves, especially us who engage with research in mathematics education or with teacher education, dealing with two different distinctive discourses, mathematics and mathematics education. Students or teachers transform what they know about mathematics and about mathematics education theory into discursive objects that are used to describe teaching and learning. So they do this transformation and this learning through an activity, a discursive activity, which is, Anna Svart has called this reification. So they engage with the mathematical discourse. They create objects that can help them to describe mathematical situations. At the same time, they engage with the mathematics education theory, and they engage with this discourse that create objects that can help them to describe mathematics teaching situations. When they manage to achieve using productively those discursive objects from mathematics and from mathematics education, such reification has been achieved. So the learning for teachers includes this process of reification. That helped us to create a typology of 4 characteristics when we try to analyze the responses of teachers when they engage with classroom situations like the ones we create in math tasks. According to this typology, we are looking at the consistency in their responses in terms of how consistent a response is in the way it conveys the link between the respondent's stated pedagogical priorities and then their intended actions. What is happening sometimes in the responses is that
I'm really sorry. Typology of characteristics of what? Sorry, I missed that.
Okay. It is a typology of 4 characteristics in the competencies of teachers to interpret classroom situations,
okay,
and to describe their intended actions. So what is happening through the math tasks? Thank you for asking, because it wasn't so clear. In the math tasks, we engage them with the classroom situations. So we try to interpret how they, from our side, we try to analyze how they interpret those situations and how they decide about their intended actions. So a response that is not consistent is, for example, when the teachers say that, oh, I would like to engage my students with this activity and help them to participate. And then when they describe their intended actions, it is just teacher talking. I will say this, I will show that, and no engagement from the student's side. So this is an inconsistent response according to this typology. Another characteristic is specificity. How contextualized and specific is a response to the teaching situation under consideration? So we invite the teachers to reflect on a certain situation, which is deliberately designed to be very specific, very narrow in terms of the issues that are described, although sometimes it is open, because we want the teachers to focus on specific aspects. When the teachers respond vaguely, without referring to the specific situation, in those cases, their response lacks of specificity. When the teachers say, for example, that I would like to engage my students with more examples, without mentioning what those examples might be, without mentioning how those examples are related to the students' responses. This engagement with the classroom situation potentially will not be useful for the teacher in the future, because when the teacher faces a similar situation, may have good intentions, for example, engaging the students with more examples, but not being able to identify an example that can fit to a certain situation. The next characteristic is reification of pedagogical discourses. That links to what I mentioned earlier, the process of reification as the teachers engage with the pedagogical discourse. So, according to this characteristic, we focused on how reified is a pedagogical discourse, the theories and findings from research in the teaching and learning of mathematics that the respondents have become familiar with, and how reified those objects are in their responses. To make it more specific, when the teachers engage in a teacher training program, where they are introduced to the pedagogical discourse, some terms are introduced. I will use an example of the instrumental relational understanding, which is very common in teacher training programs, especially in the UK. When they engage with those objects, the terms of the instrumental relational understanding, hopefully they become discursive objects for teachers to describe a situation, to design their lesson. So when the teachers say that I would like my students to engage with relational understanding, the question is, the way they describe their intended actions, for example. Is this relational understanding visible in this design? Have they reified this term in order to design their lesson, to interpret their lesson? So this is what we are looking at. It is the engagement, the reification of the pedagogical discourse when they interpret classroom situation and when they design their actions. And of course, we cannot leave mathematics out from our characteristics. It is the reification of the mathematical discourse. how reified is the mathematical discourse that the respondents are familiar with through their prior mathematical studies or through the course they attend. Again, when they interpret student responses, or when they plan their teaching actions, how the mathematical objects are used, how have they been reified in order to be to use productively in their mathematics teaching discussion. To use an example, when there is a discussion around fractions and decimal numbers and rational numbers, how those mathematical objects are used by the teachers. What they have learned about fractions, decimals, rational numbers has been reified in a way that can be used in their reflection on teaching and their teaching planning. So, going back to the theoretical perspectives, moving across this discussion on the mathematical and pedagogical discourse, teachers' capacity in identifying, interpreting, and acting upon students' needs is connected to teachers' capacity in noticing. There is a lot of work in teacher noticing. From this work, we take the a more recent shift on teacher noticing, that it is more has a more sociocultural perspective, and we see this noticing in the context of the teacher engagement of with the mathematical and pedagogical discourse. So this is my summary of what we do in Math Task and the theoretical terms we use and we propose. And I have a situation, a classroom situation to share now with you and invite you to engage with this situation. It is what we call the simplification task. You can see it, the whole task on your screen. You can download it on the Padlet if you want. So if it is okay with you, I would like you to engage with this task. It is a shame we are not in a class and ask you to talk to the person next to you. But I would say just take 8 minutes to read through, to think on the questions, to try to prepare for yourself some responses. If you want, you can type some of those responses in the chat or in Padlet. I will go through some of the findings from the use of this task in our research, and then in the final part of the presentation today, we can discuss your thoughts. So 8 minutes, is that okay? Okay, I think for the sake of time, we need to open the discussion. I can see that there are some notes on the Padlet. Thank you so much for adding your thoughts. Is anybody who wants to share some thoughts live? Otherwise, I can go through some of those comments. Yeah. On my screen, I cannot see the names, but this is not a problem. Ben, do you want to say something?
I think I've said a lot already in the Padlet, and I've said a lot before as well. So let's just Let me wait a second.
Okay, I would like to respond.
Yes, please.
Yeah. So I would like to encourage the both students, student A and student B. Okay. So here the student A doing lot of mathematical work like the multiplications and square. It's a difficult task for the year 10 students. So they are doing 2.8 into 2.8. It's a bit difficult. If they are no, if, for example, 1.2 into 1.2, 12 times of 12 equal to 144. If they are regularized and memorized or by heart things, then it is bit easy for that kind of students. Otherwise, it's quite difficult. For example, if we change the number p equal to 2.75, then what happens? The student A has a bit number of computations he has doing. So, but what student B doing? He is thinking that is we can simplify the expressions like 3c times of c. So there is a cancellation is available so that we can cancel whatever the things and do the simplification. This kind of work he is doing. And the student B know about the algebraic solving. So he has additional idea like algebra, how to solve the algebra kind of things. And student A don't know about the algebraic kind of things. That's a difficult. That's a comparison between the student A. The person one who don't know about the algebraic expression like that, he is a student A type. The person who know algebraic solve kind of things is a student B type. That a way we can categorize the student A and B in my point of view. Thank you.
Thank you, Kartik. And thank you for also for doing this comparison between the two approaches from student A and student B. So you unpacked what the mathematical part behind the two solutions. One student student A does complicated calculations correctly and ends up with the right response. Student B does the algebra, simplifies the response, and ends up with very easy calculations. And I can see in the comments in the Padlet also that that both methods can work well. The students need to communicate the different solutions and have the chance to judge each other. So we have a situation here where different approaches to the same mathematical problem, there is an opportunity of discussing different approaches. The one of the responses in the Padlet mentions the socio-mathematical norms, and this is an important aspect in this activity because what we see here is what is acceptable, how a problem can be approached in the classroom. So it has to do with the norms related to the mathematical activity. So there are socio-mathematical norms here, spot on. And the discussion with the students and the comparison between the solutions, again, that has to do with the socio-mathematical norms. And details about the task and how the different the values of the variables can work, changing the values of the variables that opens more opportunities for tasks and seeing variations of these tasks. That's brilliant responses, actually. Okay, the arithmetic and algebraic operations. Advantages and disadvantages in those two approaches. That's brilliant responses. Thank you so much for sharing.
But you kind of gave us the answer, because you said that the 4 characteristics of noticing you work with are consistency, specificity, reification of pedagogical discourse, and reification of mathematical discourse. So I guess everybody has tried to meet those criteria.
That's good. Actually, that's good because sharing what we are looking at helps people to follow the rules. So these are our norms in this discussion. So I haven't thought about this. Setting the rules beforehand drives the discussion. Thank you. I said the usually we use the characteristics afterwards. That's a very good point, actually. What I found very interesting in the responses here is that what is happening in this situation, and this was at the heart of our design. Let me tell you a few things about our motivation in designing this math task. This math task was designed after a comment. I try to change my slides. Give me a second because the buttons do not work. Okay, I'm here. Okay, this math task was inspired by a colleague who was responsible, Gareth Joel, who was responsible for teacher training in our school at that time. And Gareth said that I train my teachers and then they go to the classroom and although they have very good ideas, they want to do brilliant things with their students, they cannot do it because they spend so much time in managing the classroom and managing students' behavior. So if you spot this part at the bottom, when student B says, my solution is brilliant, yours takes ages. You cannot work with letters because you are thick. You are thick means you're in students' language, you are stupid. So student B criticizes student A's solution and calls student A thick, and the other students start giggling. So there is an issue here in terms of the criticizing students' responses. Probably there is a behavior issue here in the classroom. So the idea is to put together a classroom management issue with a mathematical issue in terms of the different approaches to the same mathematical problem. The interesting thing here is that when we gave this task to teachers in the UK, I give you an example. When we gave this task to 21 trainee teachers, all the respondents, all the teachers addressed student B's ill-behaved reaction to student A. So all the participants expressed a clear priority to establish certain social norms in their classroom. They mentioned that the students' misbehavior should be addressed with disciplinary measures. Some of them mentioned punishment approaches, consequences, sanctions, warnings, sent out, exclude from the class, peer courts, detention. All these are words that were used by the teachers who reflected on this situation. But in terms of the mathematical aspects of the incident, especially in relation to the value of the two approaches of the problem, and the potential difficulties of student A with simplification. There was an opportunity for teachers to reflect on the socio-mathematical norms they would establish in their classroom, as you have spotted. In terms of this aspect, 11 out of the 21 responses included evidence of at least one of the following. The two solutions are not of equal value. Student A has difficulties with algebra. A response that addresses student A's difficulties. The rest of them consider the two solutions of equal value. And although 3 of them mention that student B's solution can be seen as quicker, they do not address student A's difficulty with algebra. So we see an unbalanced approach dealing with the behavioral issues, but not dealing with the mathematical aspects of the situation. And this is in terms of the responses of these 21 pre-service teachers who were attending a teacher preparation course in the UK. If we have used this situation with groups of teachers in Brazil, in Greece, with you now, and the attention of the teachers is different. In some occasions, teachers focus more on the mathematical aspect and less on behavioral issues. So that supports our argument that a teacher's attention, teacher noticing, is situated in terms of what they have learned to do, how they have been trained, how they experience the mathematical teaching in the context of the institution they act, in the context of the school or in the context of the teacher training program. So I feel that I have to approach a closure, and at least to allow some minutes for open discussion. So that was a brief of what we do in MathTask. And in terms of our current work and ways forward, we have been using situation-specific tasks, MathTask, in research, in teaching, and in teacher education. For example, in undergraduate master's level courses on mathematics education, I offer a module on mathematics education for mathematics students, year 3 students. Elena offers a course on mathematics education for students who attend an education course. In my students potentially will become math teachers at secondary level. Elena's students potentially will become teachers in primary schools. We use MathTasks to introduce the students to the mathematics education language. And we use the MathTasks also in the assessment of the students at the end. We use MathTasks in initial teacher education courses. For example, we have found that reflection on teaching practices, development of noticing skills for teachers who go for school placements or who offer a trial of teaching in schools in practicum context. Engaging with those tasks helps them to be alerted, to develop the skills to notice students' needs and to plan their actions. In in-service teacher professional development courses, also we have used the MathTasks in workshops or school-based or university-based teacher courses. The classroom situations that are in MathTasks, we started with creating those ourselves, the researchers, But then we ask teachers to create their classroom situations, and we have cases where we co-create classroom situations, teachers together with researchers. Now we have moved to use some of those activities to transform them to students' activities. And in connection to teacher reflection, last year we had some trials when teachers tried things in their classroom, and then they brought those activities in a discussion with other teachers. The mathematical problems, the classroom situations are designed for or adapted to address certain educational levels, context, and specific foci. For example, when we engage with teachers in Brazil, we cannot use some of those activities and classroom situations we have designed with UK or Greek teachers in mind. We adapt the situation in their education context. And also there are different foci when we design those situations. For example, there are math tasks for mathematical inclusion for students with disability. There are math tasks that with attention on the use of digital resources. There are math tasks that colleagues in Brazil have designed and used with attention to the integration of the history of mathematics in mathematics teaching, etc. So I will close here to allow some time for discussion. I think we have 5 minutes left. So Barbara, if you want, you can switch off the video recording. But before closing the video recording, I would like to thank you. Apologies for my pronunciation. Well, Jackie, if that is correct. And this presentation will be available in the website and the video if you want to return to this. And I have also some indicative publications at the end for your reference. And I'm open to any question you may have. You can email me directly or any of us in the Math Task group.